Okay, so one more time, for those of you watching at home, so this is called the integral sign, okay? F of x is called the integrand. That's not anything that you're really going to ever worry about. We are going to talk a lot about the limits of integration because those are going to change. The a and b is going to change. A is the lower limit. That means it's going to be the one on the left, usually. B is the upper limit, so it's going to be the one on the right. And then again, muy importante, the symbol dx has no meaning by itself. You've seen that in derivatives, and so you want to attach a meaning to it. But this whole bad boy right here is all one math operation, so you can think of that as being the same as like a plus sign or a times sign or something. It's just more complex than that. And then when we calculate an integral, we are doing integration. Okay?
Yeah.
All right, note number 2. The definite integral from a to b of a function is a number. It does not depend on x. All that's saying is, what is the area underneath the curve f of x from a to b? So you could put any letter that you would like in there. You could have a t, you could have an r, you could have theta.
So you just say
You
that
can call me ray, you
doesn't have
can
to
call
be
me
x.
j. Right. Just like when you make an equation or a function, usually you say y equals 3x plus 7. But you can say w equals 3.
But you don't do that.
Doesn't matter, okay? So we can change the letters, and we're not changing the value of the integral itself, okay? Note number 3. The sum from here to when we add up all those things that occurs in our definition is called a Riemann sum, after the German mathematician Bernhard Riemann. So definition 2 says the definite integral of an integrable function can be approximated to within any desired degree of accuracy by Riemann sum. So you can say to me, Mr. Aldrich, I would like to know the area underneath this curve to the nearest hundredth. And I could figure out, actually I couldn't because I don't know how to do it, but this guy could figure out how many rectangles you would have to use to get it to be within 100th. And then you could say, not good enough. I would like it to be within 1,000th. And we could put more right. And you could pick any range that you want, and you could get within that, okay?
Red mom.
All right?
Write that down.
What? No, we're advisory today. All right. This is important also. Hey, focus. We're looking at you, Rudolph. If f takes on both positive and negative values, as in figure 3, then the Riemann sum is the sum of the areas of the rectangles that lie above the x-axis and the negatives of the areas of the rectangles that lie below the x-axis.
So what does that mean?
So what that means is,
So
I'm telling you right now, that you can get a negative answer to an integral problem, okay? It's not then the area, okay? Then you're saying this is above the x-axis is positive and this is negative.
So what
If
is
you want to actually find the area, and we'll deal with this later, then you need to make this be positive also and add those together. Okay, there's a way that you can do that. But when you're taking an integral, you're saying above is positive and below is negative. So even though you're using area as your concept to build it, you can still come up with a negative answer. And we will very soon. Okay? All right, so that is important.
So a sine function would have 0.
Right. If you did it over the right interval, right, from 0 to 2 pi, because there's the same amount below as there's above. Yes, if you did the integral from 0 to 2 pi of sine of x, you would get 0 as an answer. Excellent. Very thoughtful comment. All right, note number 4. And this is for Gabe also. Although we have defined the integral by dividing a and b into subintervals of equal length, there are situations in which it is advantageous to work with subintervals of unequal length. For instance, in exercise 14, did you say you looked at that? Because you were, okay. In section 5.1, NASA provided velocity data at times that were not equally spaced. And so in that case, they made, to solve that problem, which we didn't do together, they made rectangles of different widths because it was just easier that way. Okay, but generally speaking, you would like them to be equal width.
But you're just adding them all together, so it doesn't really matter.
Correct. Note number 5. We have defined the definite integral for an integrable function, but not all functions are integrable. The following theorem shows that most commonly occurring functions are in fact integrable. I think there's supposed to be a T there, yeah. It is proved in more advanced courses. So somebody mentioned this, I think, before we were talking about if there's asymptotes or something like that. So for us to be able to do this, we need to have a continuous function, okay? All right? Okay, so now we are done with that, and then we can, this is a little theorem here. You don't really need to write this down, that's not that important. We're not going to use this that much, okay? The main thing to pull from here is that the subintervals that you're going to use for your rectangles is going to be the total width divided by the number of rectangles. And to find the little dudes that you're going to plug into the formula, this is what Taylor and I were kind of talking about at the beginning of class. Since each rectangle had a width of 0.5, you plug the first one in, and then you add another 0.5 onto that, and then another, to get your next x that you're plugging in. Randomly, the asterisk is gone. Let's move on. All right, let's express that crazy thing as an integral on the interval from 0 to
So you put pi.
All right, are you ready? Don't blink, because if you blink, you might miss it. Here's the answer to this problem. Terrible.
Pi on top.
Terrible. I haven't done these since, last year. So 0 to pi.
Oh wait, you write it on top and on the bottom. I thought you were
This
going
is
to
this.
this side
Okay,
of
good
it.
thing we're having this talk. X cubed plus x sine of x dx.
Is it more of a
Done.
preference thing?
Is it more of a what?
Because like when we wrote it before, it was kind of like off to the side. Just how we want to do it.
I'm not really worried about how you want to use for it or how your s's look at all.
Is your acid on the bottom?
Yep, so the 0 goes to the bottom, so if we're going from here to here, this is the lower limit, this is the upper limit, okay? It goes from here to here, and then these things just all become regular old x's, and the delta x is a dx. Okay, so easy peasy, yes?
No.
Yes. All right, now, this is the one section that we're going to, and I probably won't even make you guys do this, but we're going to actually look at an example or two of solving integrals where you're actually like doing the formula. So we did one of these examples for the x squared thing when we started, and we used this formula right here. And you guys were all freaked out and were like, oh, that only does that work for da 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 da. Okay, well here's the formula for just plain old x, adding up. If you add up 1 plus 2 plus 3 plus 4 plus 5, this is the formula we use for that. 1 squared plus 2 squared plus 3 squared plus 4 squared, this is the formula for that, and this is the formula for if it is cubed. Okay? You don't have to write these down, but we're going to use those in an example here in a second. Okay? Here is some stuff that's pretty easy to figure out also. If you have just a plain old number, so if your formula is you want to go from I equals 1 to 7 and it's 5, then that would be, that's a I equals 1. 5 plus 5 plus 5 plus 5 plus 5 plus 5 plus 5, 7 times, right? And the shorthand way to do that is just to multiply the number of times you're going to do it times the number that you started with. Okay?
Where did you get the 5?
I just made it up. So that was an example.
I don't understand what that notation even means.
That means you're going to start at the first term, and you're going to go till the 7th term, and this is your formula.
5.
Yes.
Okay.
So that's a boring one. Okay? This is saying if you have a formula, let's say you want to start from the first one and go to the 5th one, and your formula is 3 times x. Instead of plugging in 1 and then 2 and then 3 and then 4 and then 5 into this, what this is saying is you can take the constant out and just add up 1, or I'm sorry, this is x, so add up 1 plus 2 plus 3 plus 4 plus 5, and then multiply that whole thing by 3. Yeah, none of this is like, it looks very complicated, but it's not at all rocket science, okay? This says you can take two formulas that you're adding together and break them up into two pieces, and this says you can take two that you subtract and subtract those, okay? Oh, thank you. All right, so let's try one of these with, we're going to evaluate the Riemann. Well, we've done this already, okay? So all you need to recognize here, we're not going to actually do this together. It says taking the sample points to be right endpoints, and A is 0, B is 3, and the number of rectangles is 6. So what we want you to be able to pull from this is, what would the width of my rectangles all be? It's going to be 0 to 3, and I'm going to have 6 of them, so it's going to be 0.5, okay? And then, what? Oh, okay. I thought you said y. And then if I'm going to have right endpoints, and each one has a width of 0.5, my first thing is not going to be 0 because that's on the left, right? So my right-hand endpoint would be, the first one will be 0.5, so I would figure out what f of 0.5 is, plus, what will my next one be? F of 1 plus f of 1.5 plus f of, whoops, 2
All the way
plus,
to 6?
no, all the way to 3,
Okay.
plus f of 2.5 plus f of 3. And then I would figure out what that is, and then I could do that from there. Okay?
And it is the number of rectangles?
And is the number of rectangles, yeah. Okay, and then for B, and I think, did I paste this in here? Okay, no. For B, they want us to do this using a limit and this cube formula right here. What do you say we just did? All right, because that gets a little crazy. All right, so notice that f is not a positive function. Notice that f is not a positive function in the one that we just did. And so the Riemann sum does not represent the sum of areas of rectangles, but it does represent the sum of the areas of the gold rectangles. In your book, they're gold, above the x-axis, minus the sum of the areas of the blue rectangles below. So this one actually comes out to have a negative answer, okay? So they're not saying that the area is negative. That's your answer. You circle it. Let me do the next
No,
one.
but like,
What units is it in?
Unit squared, unless it's like an actual table, and then they would be, square feet. You're finding the area of the infinite number of rectangles added together in this curve. So you're finding the area of this, and you're finding the area of this, and then since this is negative, you're going to go this minus that. Okay? It'll become more clear when we get the simple formula. Oh, okay, so here's the work to do that part B. And so you can see they use that cube formula in here from the other page and figure out a limit, and you get negative 6.75 would be your exact answer if you did. What's that? Yeah, right. All right.
It's all downhill from here.
It's all downhill from
man.
here. Okay, so then Taylor, like I said, so what we are figuring out when we're doing that calculation is we're figuring out what is the area of this, what is the area of this, since that's below, you subtract it, and in this case you would get negative 6.75, okay? A much simpler method for evaluating the integral in example 2 will be given in section 5.3. So I'm not going to make you suffer through those. We'll just do the easy thing, okay? All right, let's see. Can we do this? Set up an expression for the integral from 2 to 5 of x to the 4th dx as a limit of sum.
Oh, so is that
So the whole formula thing? Yeah, so what would we do for this one?
you put the 2 on top?
The
X equals,
N.
I equals 1.
I equals, in this case,
At 2.
2.
Because it starts
5,
at 2.
right, it starts at 2.
Wait, I thought,
I need to write.
Let's go back to our, again, this isn't really that important.
no, but it is.
So we're trying to write it in this thing right here.
But N is on top of the.
Oh yeah, I screwed that up.
Yeah, you
You don't use this very much. Okay, sorry, so we're starting out, that's going to be a limit of sums. So we need to limit,
Or right in your word right there.
yeah, as n approaches infinity of I equals 1 to n. So we're going to add up an infinite number of rectangles. Right?
Wait, is I equal 1 or is it 2?
No, that is going to tell us
We're going
this.
up by 1, that's the next, right?
Right. So we want to do, what is our, if we're going from 2 to 5, that has a width of 3. So the width of all the rectangles would be 3 over n, right? Okay. And then we're going to take those to get the y values and plug them into the formula. So this was our 3 over n. Well, we can just go f of 3I over n. Call it there.
Where's the x?
Yeah, where's the,
Where's the what?
Well, that's
X to the 4.
That's the f, yeah, is the x to the 4. Okay. So if you want to take it a step further, you could get rid of this thing right here and make that a 4. You like that better? Okay. All right. So that's the general idea there, and we're getting closer and closer to, as I said, we will learn a much easier method for the evaluation of integrals in the
I'm here.
next section.
Are we done?
Okay, we are done for the day.
No homework?
No homework.